We'll now begin talking about polymers. In this first video of this section, we'll talk about addition polymers. Okay, first of all, what is a polymer? So a polymer is a very, very large molecule that is made up of several monomers that are all bound together. So what's a monomer? The monomer is the smallest repeating unit of the polymer. So you just take a bunch of monomers and you link them all together, and that makes a polymer. We'll take a look at an example here. So an example of a monomer might be tetrafluoroethylene, or you could also call it 1122 tetrafluoroethene. That would be the systematic name, but the common name for it is just tetrafluoroethylene. Now, what you'll recognize is that in this molecule, you have a double bond between the two carbons. What you can do is break the pi bond. And in doing so, there are now only 3 bonds on this carbon, 3 bonds on that carbon. They're both free to make another bond. So this carbon on the left is free to make a 4th bond to another polymer unit to the left. That extends the chain in that direction. And the carbon atom on the right is now free to also make another bond to another monomer unit, extending the chain rightward. All right, and so when you polymerize it, this is what you're going to get as the structure for your polymer. Right, you saw here we broke the pi bond, freeing up this carbon to make a 4th bond to another unit going to the left. You broke the pi bond, freeing up this carbon atom to make a 4th bond to another monomer unit going to the right. And so this unit gets repeated again and again and again, n number of times. That's why we put the whole thing in brackets and then just put n here. We call this polymer polytetrafluoroethylene, and the kind of trade name for that is Teflon, a very important molecule that's used as a nonstick coating for pots and pans. In a polymer, we're not just going to draw this monomer unit being repeated over and over again. That would take up way too much space, and there's no reason for that. Just like when we talked about unit cells in chapter 16, once we have the smallest repeating unit, we can just look at that and then just say that's being repeated over and over again, and then you can recover the full molecular structure of the polymer. We just put the repeating unit in brackets and then say that it is repeated n times. Now, what we just saw in the last example was something called an addition polymer. This is a polymer that's made by adding several monomer units together. And in the process, no atoms are being lost. So I'll just go back to show what I mean by that. Right? All that we did in order to extend the chain was just break a pi bond. We didn't eliminate any atoms from the monomer unit in the process of making an addition polymer. All we're doing is just adding one of these to another one, to another one, to another one, and no atoms are being lost in the process. Addition polymers are made via a mechanism that's called a free radical process that involves 3 types of steps. The first is called an initiation step. That's what gets the reaction started. The second is called a propagation step, and that's what allows you to elongate and extend the chain. And then the third step is the termination step, which is what results in you ending the growth of the polymer molecule. We'll take a look at a very crude representation of the mechanism for this process here. So first we'll talk about the initiation steps, the steps that get the reaction started. Often you can start with a molecule that's called an organic peroxide. For an organic peroxide, you have some R group, O, and then there's a single bond between these 2 oxygen atoms right here, and then another O, and then another R group here. When you add energy to this, usually in the form of ultraviolet light, the ultraviolet photon provides enough energy to break this bond between the 2 oxygen atoms. Remember that a bond consists of 2 electrons. And so what will happen is when you break the bond, one of the 2 electrons goes to the oxygen on the left, and one of the 2 electrons goes to the oxygen on the right. We use these half arrows to represent that. So this half arrow represents 1 electron from the bond that goes onto this oxygen. And then this half arrow represents the second electron from the bond that goes onto that oxygen. So that will give you 2 molecules that are just ROs. These are free radicals because you have 1 unpaired electron here, right? You have a single electron that was from this bond that ends up on the oxygen atom. Now, free radicals are very reactive molecules because electrons like to be paired. And additionally, this oxygen does not have a complete octet. This oxygen will only have 7 electrons instead of 8 because you are missing an electron here. So this is going to be very reactive, and it's going to be seeking out another electron so that you can complete the octet rule. What will happen is this RO free radical can go to react with a monomer unit. In this case, I'm going to use ethene as my monomer. It's looking for electrons, and it sees electrons that are in the pi bond between the 2 carbon atoms in ethene. what happens is this RO free radical is going to try to react with ethene to get another electron. In the process, it's going to try to react with the carbon atom, and I'm going to represent that by drawing another curved arrow with a half head on it like that, right? That represents the one electron from the free radical that is trying to form a bond to the carbon atom there. But this carbon atom already has 4 bonds to it, and so it would violate the octet rule if you just made a straight up bond here. So in order for you to form a bond, you have to break this pi bond between the 2 carbons. That would be done by taking one of the electrons from the pi bond and moving it over to there to form a bond between the 2 carbon atoms. And that is what this bond is here. The 2 electrons from this bond, one of them comes from the free radical, and one of them comes from the pi bond, making that bond between O and carbon. The other electron that was in the pi bond goes onto this carbon atom, and in the process, you put a free radical on this carbon atom. Now, because you've regenerated a free radical now on this carbon atom, you've allowed the cycle to be able to repeat itself, because now this molecule can find another ethene molecule and perform the exact same reaction to elongate the chain going to the right. And so this starts the propagation process. So now let's take a look at the propagation steps. And here we can see an animation of it. Right, so that shows how you're able to have monomer units react with one another, and the process propagates because every single time that you perform the reaction, you form another free radical, allowing the cycle to repeat. I'll just show it one more time. All right, so there you go. So you can kind of just see the mechanism play out here. All right, hopefully that all came through really well in the video. Now, will this process be able to go on forever and you'll just be able to make an infinitely long polymer? That's not going to be possible for us. So what ends up happening is, after a while, you'll no longer be able to propagate the polymer and you're going to reach a termination step. And this occurs when 2 radicals find one another and react with one another. And in the process, they neutralize one another. When they react and combine, you will form something that is not a free radical. All right, so let's take a look at an example of a termination step. So here we have one free radical, right? So that could be some polymer chain, and this could be a second polymer chain. It's a free radical because it also has this unpaired electron. I do want to point out here that this thing up here is a prime. It's not another electron. This is something that's indicating that this R group is different from this R group. So we have that this electron can pair up with this free radical electron, making a bond, right? 2 electrons make a bond. And now we have our R group, and then this is again R prime. And so we've now neutralized the 2 free radicals with one another, and we've now formed something that is not a free radical, and it is no longer reactive. And so at this point, the polymer does not grow any further. And in this case, these can be any free radicals in the reaction. So it could be another OH group. It could be an OR group from the organic peroxide that you split using light in the initiation step. It could be another polymer chain. It could be anything. But anytime that 2 free radicals pair up with one another and bond together, they neutralize one another, and you cannot perform any further growth of the polymer at that point. Now, addition polymers are what are known as homopolymers because they're made up of just one molecule that is repeated over and over and over again. And on exams, the really important thing for you to be able to do is to identify what the monomer is if you're given the structure of a polymer, or if you're given the structure of a polymer, be able to figure out what monomer was used in making it. So let's take a look at a couple more examples, right? We already saw the case of polytetrafluoroethylene. And we also just saw the mechanism for the polymerization of ethylene to make polyethylene, right? We saw how you take C2H4 and you perform that free radical polymerization process to link a bunch of these molecules to one another, forming the polymer here. Remember that in order to do that, you must break the pi bond, right? So if you didn't do that, you would have 5 bonds to carbon, and that would be very sad. So break the pi bond, and then you can elongate the chain going to the left and to the right. Just for a few additional examples, we could talk about what would happen if you took propylene and polymerized it. So here we've got the double bond between these 2 carbon atoms. You break the pi bond, and then that allows this carbon to make more bonds to other units going to the left, just like this. And it frees up this carbon atom on the right to make more bonds to other polymer units going to the right. So there's that. And in the process of doing that, you form polypropylene, which is a polymer that's used in a lot of plastics. Oftentimes, you'll see polymers used in the plastics industry. And so we work with polymers in our everyday lives all the time. We'll take a look at one last one when we talk about styrene. So The double bonds that you have in benzene are all very stable due to the resonance delocalization that occurs here. And so it's not going to be these bonds that end up being broken. It's going to be this pi bond that gets broken when you perform polymerization. So you break this pi bond, there's 2 carbons here, right? And that forms the backbone of the molecule, right? So these 2 carbons is this 1 and 2 carbon here. You break the pi bond, right? So there's only now a single bond between the 2 carbons, and then you can extend the chain going to the left and to the right. And that takes styrene and turns it into polystyrene, which is used in making styrofoam. Now, as you can imagine, these bonds are fairly strong, and it's for this reason that polymers and plastics don't biodegrade very easily. And so that has some consequences for the environment, and it's important to be aware of those. And one of the nice things about taking a chemistry class and getting to learn about these polymers is being able to see why it is that polymers are so stable. And why it is that they don't biodegrade. And you can get an idea for that by knowing some of the things that we've been talking about here in this chapter when we've been discussing organic chemistry. And so again, make sure that you look over these examples very carefully and practice with them so that you can get familiar with how to predict what the structure of a polymer is based on what the monomer is. Or you could also look at just the right-hand side of the slide, covering up the stuff that's on the left, and be able to go backwards from what monomer made up the polystyrene to know that, okay, if you wanted to go back to the monomer unit here, you would have to break the bonds to the neighboring monomers in the chain and then form a pi bond to go back to the original structure of the styrene that you would have started with. So be able to predict both ways in the reaction, how to go forward and also how you would go backwards to predict what monomers made up the polymer. Up next, we're going to talk about condensation polymers, which is a different type of polymerization, and it's going to be made through a different type of chemical reaction.